So thanks for the invitation and thanks for coming. So yeah, I'll talk about order-preserving Martin's conjecture, which I don't expect everybody knows what that means. So we'll start with that, and then we'll see that there's a connection to intermodel theory. To be frank, it's like a planned connection, really. So there's a lot of work to do, but I think it's an interesting connection. Yeah, and this is all joint with Patrick Lutz, and then some of it is also some folklore results or results from Lehman and Steele. Okay, so yeah, so just some background. So first, just Martin's conjecture more generally. So there's an observation maybe made by Martin and other computability theorists. So there seems to be significant global structure to functions on the Turing degrees that come up naturally in computability theory. So the ones that computability theorists identified. And Martin's conjecture is just a precise way of stating that the global structure is as it appears. And very roughly, the conjecture, the precise statement is that under a determinacy hypothesis, in the context of the axiom of determinacy, functions on the Turing degrees are, up to minor variation, just constant functions, the identity, and iterates of the Turing jump. Just some basic computability theory notions. I don't think that everybody here is so familiar with computability theory, or you're maybe somewhat rusty on it. So okay, just to get everybody on the same page. So okay, so I'm going to use this less than or equal to sub t for Turing reducibility. So x is Turing reducible to y if and only if x is computable from y. So via, let's say, a Turing machine that uses y as an oracle. And x is Turing equivalent to y if x is computable from y, and vice versa. A special kind of set of reals we'll think about a lot is called a cone, or cone of Turing degrees. Okay, and so that's a set that has this special form, all the reals that are Turing above some base real b. All the reals that compute some real b. Called a cone. So we'll call a set of reals Turing-invariant if it's closed under Turing equivalence. And we'll call a function from the reals to the reals Turing-invariant if it sort of respects Turing equivalence. So if x is Turing equivalent to y, then f of x is Turing equivalent to f of y. Yeah, and just an observation. So I said we're going to be analyzing, Martin's conjecture is about functions on the Turing degrees, but then I'm immediately leaving that. But let me just point out, right, a Turing invariant function in this sense clearly induces a function on the Turing degrees. And okay, under the axiom of choice, we do have that every function on the Turing degrees arises in this way, but we're going to leave the choice context, but it also holds under 80+. Okay, so the sort of motivating theorem to get things going is due to Martin. So this is Martin's cone theorem. So assume AD, then any Turing invariant set of reals either contains a cone or is disjoint from a cone. The way this is sometimes thought about is that if you look at the Turing invariant sets of reals, there's a filter that's an ultra filter for the Turing invariant sets of reals that it's just generated by the cones. So one more definition, then we'll state Martin's conjecture. So for Turing invariant functions f and g, put f is Martin below g if and only if f of x is Turing below g of x on a cone of x. And similarly, say f is Martin equivalent to g if f of x is Turing equivalent to g of x on a cone. So it's the natural equivalence modulo this ultrafilter that I mentioned. Okay, so here's a statement of Martin's conjecture. So it was stated, I believe, in the 70s. I'm not sure. But so the hypothesis maybe looks a little weird now, but it's under ZF plus AD plus DC. I think probably if it were thought of first now, maybe it would be under AD plus. In any case, okay, assume ZF plus AD plus DC. The conjecture is that two things hold. So part one, for any Turing-invariant function, either Turing-invariant function f, either there's a constant c such that f of x is Turing equivalent to that constant on a cone. So that's f is constant on a cone. Or f of x is Turing above x on a cone. F of x computes x on a cone. So that's f is Martin above the identity function. Okay? So that's part one of Martin's conjecture. Part two is that this relation that we've defined actually pretty well orders the Turing-invariant functions that are above the identity on a cone, or above the identity in the Martin order. So pretty well orders the Turing-invariant functions such that f of x is Turing above x on a cone. Moreover, the successor operation in this pretty well order is just given by composition with the Turing jump. Okay, and I wanted to draw a little picture. Oh, first, just in case, I think, I don't know that everybody's seen like any computability theory, so let me just remind you some notation. So when I say the Turing jump, I mean the function x goes to x jump, as it's referred to in computability theory. So this is, the recursion theorists think of this as the halting problem. Way bigger. The halting problem relative to x, so using x as an oracle. Okay, but maybe something that's more accessible to this audience, right? We can think of this as a universal sigma 0, 1 subset of omega. Of x, thank you. Okay, so when I say the Turing jump, or the jump, what did I say? Yeah, the Turing jump, I mean this function. Okay, so here is the picture of the degree invariant or Turing invariant functions under Martin's conjecture. So we have I don't know, something that looks like the question. Yeah. Thank you, Lena. Great, thank you. Okay, so we have the constant functions. Which is the same thing as, right? There's one for each constant, so it looks to, or looks like the Turing degrees. Okay. Above all the constant functions, we have the identity, and then after that, we just iterate the Turing jump. So we have, okay, after that, we have the very next thing is the Turing jump. Okay, what's after that? I said we compose with the Turing jump. So we have what they call the double jump. Okay, so that's the jump of x jump. Okay, and so on. So there's a transfinite version of the Turing jump, but we'll see there's other familiar examples that we'll think of as transfinite iterates of the jump. But I do just want to introduce one more bit of notation that people may not be familiar with. Like this, so recursion theorists write use this notation. So if alpha is an x computable ordinal, don't worry about that. Then we write x to the alpha to be with parentheses to be the alpha if iterated Turing, which is well defined in this under this hypothesis I mentioned. Okay, anticipating a little bit, I want to just make one more definition that people are probably familiar with. So one more special real number that we're going to look at is Kleene O relativized to X. Which is sometimes in computability theory the hyperjump of X. Or for this audience, perhaps, universal pi 1, 1 of X subset of omega. Okay, I think that's all the computability theory we'll need. Any questions about the picture? So again, the picture is the constant function is the identity, and then part 2 is about what happens above the identity. It's this pre-well order with successors given by composing with the jump. We'll talk about that hopefully in the last minute of the talk. But yeah, it's that. What's the omega second? Okay, we'll talk about it. Okay. Oh yeah, okay, and I guess, yeah, lights off. Thank you. So yeah, both parts of this conjecture are open. And very much so, they're open even for Borel functions, but there have been partial results. So Slayman and Steele really, Steele for part 2 and Slayman and Steele for part 1, showed both parts of the conjecture hold for what are called uniformly Turing-invariant functions, which is strong evidence for the truth of the conjecture. I'm not going to define uniformly Turing-invariant functions, but this is essentially explanatory of the observation by computability theorists. So all the natural functions are actually uniformly Turing-invariant. Okay, but in this talk, we'll consider Martin's conjecture for a different class of functions. So we'll consider Martin's conjecture for the class of order-preserving functions, which turns out to be more tractable. So yeah, a function, I'm going to make the natural definition. So a function on the rails is order-preserving if it's order-preserving with respect to Turing reducibility. So if and only if x is Turing below y, then f of x is Turing below f of y. So Slayman and Steele showed the following. So assume just ZF, I think. Then part 2 of Martin's conjecture holds for Borel order-preserving functions. So there's the analog for if you drop order-preserving is open, I mentioned. Okay. But for order-preserving functions, they showed part 2 holds, assuming the functions are Borel. More recently, Patrick and I showed that part 1 holds for order-preserving functions. This is just a statement here. This second theorem is part 1 for order-preserving functions. So it says, under AD, for any order-preserving function, either it's constant on a cone, that's option 1, or it's above the identity on a cone. Is which? Oh, no. For order-preserving? No, sorry, yeah. It was up very briefly. It's for Turing reducibility. Yeah, no, yeah, that order is definitely irrelevant. Okay, and yeah, and combining these two results, we do get both parts of Martin's conjecture for Borel order-preserving functions, and moreover, this is actually just provable in ZF. Okay, so what's left then is part 2 for order-preserving functions beyond the Borel functions, which I think computability theorists, are find less compelling. But we'll see. I think it's very interesting. Like set theory comes into play much more for these functions. Okay. So in the talk we'll talk about some recent progress on what remains of part 2 of Martin's conjecture for order-preserving functions, and then the thing I really want to talk about is a plan for proving it order-preserving part 2 in general. Not quite in general, but under a mouse capturing hypothesis. Okay, so we just saw Slayman-Steele showed part 2 holds for Borel order-preserving functions. They actually showed a bit more, so this is their theorem. So assume AD. Let f be an order-preserving function that's above the identity. Then either f is one of these alpha-th iterated Turing jumps on a cone for some ordinal alpha less than omega 1, or f is above the hyperjump, Kleene's-O relativized x on a cone. Either you're one of, so what it says is everything is comparable. Maybe you should think of it this way: everything's comparable to the hyperjump. Everything order preserving is comparable to the hyperjump, and the things strictly below the hyperjump are just the plain transfinite iterates of the Turing jump. I should mention, So the plan is just, maybe should Q be, okay. Yes, okay, thanks. So the hyperjump part is, so I should add wood into this. So we'll see our work and this plan I have all revolve on just sort of naively generalizing the proof that they give, which involves generalizing the Posner-Robinson theorem. So in this instance that John's rightfully crediting Hugh with, we need the Posner-Robinson theorem for the hyperjump, which is due to Wooden. Okay. Yeah, again, the plan is just generalize, like do their proof in general. Okay. So I'm just going to talk about a special case where this was successful, and also how it might go in general. So okay, so recently we Patrick and I proved the following. So assume AD, let f be an order-preserving function that's above the hyperjump. Then either, okay, brace yourself. Either f is the hyperjump to the sigma of omega 1x jumps on a cone for some function sigma from omega 1 to omega 1, or it's above the double hyperjump, the twice iterated hyperjump, so O to the O of x. Okay, I think it's a little hard to parse, but yeah, I didn't write it that way. I will mention this. Yeah, it's not obvious that this is not immediately obvious that this is a version of Martin's conjecture for order-preserving functions up to the double hyperjump. But yeah, we can. Yep. Yeah. But not forever. Maybe you can ask me later. I can do some transfinite. Okay. Yeah. So it's a little difficult to state, but now I meant to do one more thing. I know the light's off. Let me not write it, but this omega 1 superscript x, that's the Church-Kleene ordinal relative to x, the least x admissible ordinal. Question? Oh, great. Okay. Great. Yeah, I hope, almost surely I'm not going to have time to say. I can tell that now, but it will be, it's in the slides. I hope to be able to say something. Anyway. Okay, so let me just give another definition to sort of explain, I think, like what Gabe was asking, like how this is about order preserving Martin's conjecture. So say that a function g from the reals to omega 1 is Turing-invariant if when x is Turing equivalent to y, g of x is actually equal to g of y, right? So they're ordinals. And we'll do the same thing and use Martin's cone theorem to do the obvious ordering on these Turing-invariant functions into omega 1. So put g as Martin below h if g of x is it's an ordinal less than or equal to h of x on a cone. Okay, so Martin's cone theorem implies that Turing-invariant functions like this are pretty well ordered by the Martin measure. Okay. And then since functions of the form mentioned in the theorem, so what function am I talking about? So the function x goes to, so we have sigma goes from omega 1 to omega 1. We have the function, we're looking at x goes to sigma of omega 1x. That's a Turing-invariant function. Our theorem implies part 2 of Martin's conjecture holds below this double hyperjump because the order the order on things of this, so these things of this form are pretty well ordered by this order. The ordering on these iterates of the hyperjump is just inherited by it just comes from the ordering on the functions. And the success, maybe it's just worth saying a silly comment, like what's the successor in this order okay, if you have g, a Turing-invariant function, what's its successor? It's x goes to g of x plus 1. That's tacking on one more jump. So this theorem really does easily give you part 2 of Martin's conjecture for order preserving functions. Hello. Sadly, only a very, very small part of. You mean the point class or the? Oh, same question, I guess. Only no, not delta 1 2. It's this is down very low. Oh, sorry. I'm thinking. Oh, okay, thank you. Yeah, eventually we have to look at. Yes. That's a description of omega 2. Yeah, the double hyperjump. I asked this. Tended to ask the question, what's the thing of rank omega 2? It's the double hyperjump. Other questions? Yeah. Yeah. Oh, if it's, you mean like if, sorry, when is the question? Like that things like this have low complexity?
No, so this F in principle might have very high. I guess there's that moves.
Oh, you're asking, is this like absolute or something?
I'm asking if.
Oh, yeah. I think there's something you need to do. You don't need to do it the way that I'm going to do it today, but there is something to do. Yeah. Yeah, I think there's. Yeah. No, because sigma is just, you know, we get this is trivially Turing-invariant because sigma, you're just plugging in an ordinal. And I mean, if x is Turing equivalent to y, omega 1x is equal to omega 1y. Okay. Okay. Okay, so the perspective that I'm going to take today on this theorem is to view it as like a successful instance of this intermodel theory approach to proving part two, or order preserving part two in general under mouse capturing. And the connection is to these master code functions identified by Jensen. So Jensen, you know, used his fine structure to identify these canonical constructible reals called the master codes. Mitch Rudeminer extended these results to MS-indexed premice. So here is the theorem of Rudeminer. It's building on Jensen's proof. Okay, so let M be, and you know, many of you, at least if you were here yesterday, you know what a mouse is. Oh, you don't? Do you know what an X mouse is? You just put in the real X. Okay, so let M be a sound X premouse, and suppose there is a delta n plus 1 of M definable real, which is not delta n M definable. It's like newly definable at level delta n plus 1. Then there's one of maximum Turing degree, and it's easy to see that's equivalent to saying there's a y which is delta n plus 1 of M definable, such that every x that's also delta n plus 1 of M definable is computable from y. We call such a real a delta n plus 1 master code. Let me just, in case you're worried, for the previous theorem, we only need very basic x premise. We only need ones that are just levels of L, or levels of L of x, so of the form J alpha of x for some x. So if you'd like, if understandably some of you are not comfortable with premise, just anytime I say premouse, you'll get plenty out of this if you think, oh, it's just a level of L of x. X premouse is a level of L of x. Okay, and same here. In this statement of what a mouse operator is, think mouse means level of L of x. Okay, so a mouse operator is and this is just a certain kind, but all I'll need today. A mouse operator is a function M with domain the reals, such that on input real x, you have to spit out M of x, a sound omega 1 iterable x premouse. Remember, we're in the AD context, so I could also have just said omega 1 plus 1 iterable. And moreover, if you look at M of y and M of x for x and y Turing equivalent, you're just doing a trivial reorganization. So M of y is just the trivial reorganization of M of x as a y premouse. You maybe are not familiar. Think the levels of L. You just replace x and y. Replace x for y. Which are trivial reorganization? I mean, like technically there's a predicate for x, and you replace it with the predicate y. I mean, you should think like I haven't even. They're not reals, yeah. But it'll come up. Okay. I mean, okay. That's the next point. Oh, okay. Say M is relevant if the hypotheses of the previous results are met, so that there is an n such that there really is a new delta n plus 1 definable real. You have a new definable real. That just says M of x projects to omega, right? So a mouse operator that always spits out something that projects to omega, I'm calling relevant just for this talk. Given a relevant mouse operator, we let fm denote any function such that f of x is one of these delta n plus 1 master codes. but I want to take the least, do something a little non-standard. I'm going to take the least n, such that there is such a master code. So f of x is a delta n plus 1 master code for n least, such that there's a delta n plus 1 real, which is not delta n. It's just a bookkeeping thing, but it's convenient. And the Rudiminer theorem I mentioned before tells you that these FMs are unique up to Martin equivalence. And if you think about it, you can actually take FM to be uniformly Turing-invariant, so that Steele's theorem applies. But also, because we're demanding that everything is, we're always outputting omega 1 plus 1 iterable mice projecting to omega. If you remember from John's talk yesterday, mice projecting to omega or X mice projecting to omega are just well ordered by the initial segment relation. So we have a natural well ordering of the relevant mouse operators coming from the initial segment relation on their outputs. And it just actually exactly coincides with the order on these FMs up to the Martin order on the FMs. When am I supposed to stop? Okay, so let's see some examples. So we're going to see examples that are levels of L, and then examples that are not, and we don't need to care about the examples that are not. Okay, so here are examples of, I'm going to list some mouse operators and the associated function. Okay, I guess, I don't know, like, is H is hereditarily finite with X? Is that an X mouse? Not. Why not? Okay, but I'm skipping that one. Okay, so we're going to start with X goes to J1 of X. That's just this first, rudimentary closure of like omega union singleton X or something. What is the associated Turing-invariant function? It's X goes to the omega-th jump of X. And sort of why X goes to the omega-th jump of X is actually just a simple join of X goes to X to the nth jumps of X for all n. So this is just a join in a straightforward, simple way of X to the n for all n. I mentioned X jump is like the universal sigma 0, 1 set. That pattern continues. X double jump is a universal sigma 0, 2 of X set. And so really what's going on at the omega jump is you're just collecting together the theory of X with omega with predicate X. Okay, so that's our first instance of this. Next one, X goes to the smallest admissible, smallest model of KP containing X, so that's J omega 1X of X. What's the associated Turing-invariant function? It's just Queenie's O for the hyperjump operator. There's an important difference between these two cases. So this is like the not admissible case, and this is the admissible case. Okay, what's the next one after that? Do I do that? Yeah, okay. What's the next one after that? It's just X goes to J1 of this, that's J omega 1X plus 1 of X. And the comment I made previously still applies. So that's just essentially so this turns out is like the sigma 1 theory of this structure. And then this is just the full theory of this structure. And that pattern continues. Okay, and then how are we going to connect up to the theorem I mentioned, the main theorem? Well, what about things of this form? So X goes to J sigma of omega 1X of X for sigma from omega 1 to omega 1 non-decreasing. Okay, it looks ugly, but it's just some appropriate number of jumps determined by sigma of O to the X. So you just, maybe I should have done it with like pluses or something, I don't know. But it's just you take O of X and you do compute sigma of omega 1X minus omega 1X and multiply that by omega. do that many jumps. So it's a very simple operation. Okay, so that's the operator associated to this. Okay, yeah, and then what about the double hyperjump? It's associated to this, second admissible. Okay, and then don't think about it if you don't want to, but you can keep going. We identified lots of operators like this in inner model theory. So the most, first real one, sort of, is x goes to the pre-mouse x sharp, and the associated Turing-invariant function is just x goes to the, real x sharp, real number x sharp. Okay, and then that is totally general. If you have one of these sharp like mice, you have like M1 sharp, for example, minimal sharp for wooden cardinal. You can do the same thing. It's technically there's a pre-mouse, but there's also an associated real. This is a typo. This should say omega 1 sharp of x. Okay, so you can keep going. And notice, so I said this was a little non-standard. We're only getting the natural functions of limit rank the way I'm doing things. It's just for convenience. How do you get the other ones? You just compose with the Turing jump. Finitely many compositions with the Turing jump. Okay. Let's see. Okay, so from Slayman and Steele's work, we can identify sufficient criteria for establishing instances of part 2 of Martin's conjecture. And the criteria are like somewhat interesting, I think. So they're just computability theory theorems generalized to appropriate mouse operators. And that's sort of no surprise based on how it went for Slayman and Steele's work, though, I mean, the mouse perspective is not discussed there so much. Okay, so here's our first theorem. So this is the Friedberg jump inversion theorem. So if you have reals x and y is Turing above x jump, then y looks like the jump of something. So there is a z that's Turing above x such that y is just equivalent to z jump. Everything above x jump looks like the jump of something above x. Okay, so we can just more or less copy this and replace the jump operator with fm. So say a relevant mouse operator has the jump inversion property if, okay, and I'll say on a cone. If on a cone, whenever y is Turing above fm of x, its associated function, there's a z above x such that y is Turing equivalent to fm of z. And moreover, Friedberg's original proof for his theorem provides a general method of establishing the jump inversion property just mentioned. So suppose that, I stated it a little vaguely, but if you know the proof of the jump inversion theorem, you hopefully know what I mean. So suppose that on a cone of x, m of x join y, so you can combine two reals. So m of x join y is m of x adjoin y, in the sense of forcing, whenever y is sufficiently Cohen generic. Then m has the jump inversion property. This is essentially the Friedberg argument. We won't talk about it. So let's consider the kind of what we need for our main theorem. So consider a mouse operator m that's just outputting these j sub sigma of omega 1 x of x's. Now, if y is sufficiently Cohen generic over the structure, or I'm being a little vague what I mean, that's okay. Then we actually know that omega 1 x join y is the same as omega 1 x. Why? Sufficiently generic Cohen reals preserve admissibility. They preserve this omega 1, this relativized Church-Kleene ordinal, because it's the least admissible relative to these things. So it follows, right? So it follows, we're just plugging in the very same ordinal into this function sigma on for the relevant computation. So these are equal. And so these structures are equal as well. Internal, taking the join inside here is the same as adjoining the generic real y. So M, this M has the jump inversion property. This property is useful because it takes us through successor steps of an argument that's like trying to verify part 2, or part 2 of order preserving part 2. In what form? So here's the main lemma. So let M be a relevant mouse operator with the jump inversion property and N an integer. If G is some other order preserving function that's strictly above Fm to the n jumps on a cone, then G is actually at least the n plus first jump of, composed with Fm. You're getting up from, okay, you're strictly above the nth jump of this Fm, and you're at least the n plus first jump. That's, this Friedberg argument. Okay, so I'll just talk about one more property that'll get us through essentially the limit steps of a sort of vaguely inductive argument. So here is, I mentioned earlier, the Posner-Robinson theorem. So if we have I don't know, so I stated it maybe in a particular way, but suppose y is not computable from x. Then there's a z Turing above x such that y join z is at least z jump. You can, if y is not computable from x, then you can find a z such that joining y with z gets you above z jump. That's the Posner-Robinson theorem. Not as easy to parse as the jump inversion theorem, but the details are not so important. I just want you to get the idea. So say a relevant mouse operator has the Posner-Robinson property if on a cone for all y, cone of x, for all y Turing above x, such that y is not a member of M of x, so I've changed things a bit, there is a z Turing above x such that adjoining y with z gets you above Fn. So I've done sort of two things, right? I've replaced the jump in this last line by Fm. That's like what you expected. But then I've done something different here. I've replaced y is not computable with x, computable from x with y is not a member of M of x. Otherwise, it's a generalization. And it seems mysterious, but this is just because we took, the way Fm was defined, we took this like minimal n. It's natural if you think about it. Okay, and let me just comment, the original proof, the Posner, and Robinson's proof did not generalize. But other proofs have been found that do generalize. So the first proof is due to Wooden, who proved an analog of the Posner-Robinson theorem for Cluny's O. And later, Kumabe and Slayman found a proof that does generalize as well. So I'm going to use their method. So what you can show using their method, and almost certainly you can show it using Wooden's method as well. Well, the appropriate thing using his method as well. So suppose that on a cone of x, we have a very similar thing. Adjoining Kumabe-Slayman generic reals is the same thing as internally taking the join. So M of x join y is M of x adjoin y for sufficiently Kumabe-Slayman generic reals. Then M has the Posner-Robinson property. I meant to say I'm not going to tell you what Kumabe-Slayman forcing is. All right. It doesn't matter for what I'm trying to get across, but I know you likely want to know. It's more accessible than it used to be. So there is a paper which goes through the Kumabe, uses Kumabe-Slayman forcing to do the prove Wooden's theorem on Posner-Robinson for the hyperjump. But yeah, I don't want to talk about it. I'm out of time. And yeah, and a similar argument to what we just went through shows that the kind of mouse operators that we're interested in for the main theorem do in fact have the Posner-Robinson property. And moreover, just because it all amounts to preserving admissibility, and one can show that Komabe-Slayman enforcing sufficiently generic Komabe-Slayman reals preserve admissibility. And it's easy to see these preservation of admissibility arguments also work to show these two properties for this next one. M of x is j omega 2x of x. So that also has the Posner-Robinson property. Let me just, I'll wrap up soon. All you'll miss is proofs that shouldn't have been there anyway. Okay, so what can we get from Slayman and Steele's work? So remember, we're trying to generalize the Slayman-Steele theorem, or the Slayman-Steele and maybe Wooden theorem, I guess. So suppose M has the Posner-Robinson property. M is this relevant mouse operator. Then for every order-preserving function g, either g is in M, g of x is in M of x on a cone, or g is above the associated Fm on a cone. That's I didn't plan to give this argument, but it's a very short argument. I didn't plan to do it, and I won't do it. But it's a nice argument. Very short. Okay, and let me just say, so I won't justify it much, but these two lemmas that we saw, and these two properties really do give you I think a reasonable plan for trying to show part 2 of Martin's conjecture for order-preserving functions. This should have said part 2 of Martin's conjecture for order-preserving functions from mouse capturing. So here's the theorem that's, it's essentially just these observations that I just made. So I don't know, it should be not really due to me. So assume AD plus mouse capturing. John defined mouse capturing. It just says there are enough mouse operators. Suppose every relevant mouse operator has the jump inversion property and the Posner-Robinson property. Then part 2 of Martin's conjecture just holds for all order-preserving functions. The point is, this, I don't know, to me this seems like a plausible thing that you can try to show. And we have had some successes doing it. So this is a plan for proving order-preserving Martin's conjecture under mouse capturing. You didn't want to see that. Okay. And then let me just wrap up very quickly by saying roughly like how it goes to prove the main theorem that some of you are more interested in. So how do we get this theorem from this general mouse operator perspective? So, okay, so I just restated it here. So how are we going to do it? So let M be this j omega 2x of x operator. I mentioned that this has the Posner-Robinson property. This has the property we just defined. And moreover, it just exactly corresponds to the double, its associated function is the double hyperjump. So since it has the Posner-Robinson property, we know this lemma, I shouldn't have gone back. This lemma tells us every order-preserving function is either in that function, has this property, or it's above the double hyperjump. Okay. So in any case, all that remains is to show that if f of x is in j omega 2x of x, then actually f of x has this form. That it's one of these hyperjump to the sigma of omega 1x jumps. And someone asked, how do we get the sigma? So maybe I can answer that at least. So we just want to show that the relevant mouse operators in between here have an associated sigma. So you have a mouse operator that's spitting out an initial segment of L of x between j omega 1x and j omega 2x. Okay, so you need to show that it has this particular form. That's the theorem. A lemma, I put it. So that's the content of this lemma. So suppose you have an n in between an n like this. Suppose you have an n like this. Then notice it just has the following form. It's j sub g of x of x for some g, right? It's for some function from the real, Turing-invariant function from the reals to omega 1 that's outputting an ordinal in between these two. So all you need to do to establish the theorem, I mean, modulo some arguments, all you need to do is notice that the functions g, like this, that are in between omega 1x and omega 2x in this way, actually just have this form. Okay, and it's true. So in a sentence, why is it true? Omega 1 is the least generator of the Martin measure. Omega 2 is the second generator. X goes to omega 1x, has rank omega 1, and x goes to omega 2x, has rank omega 2. Think about it, that suffices. Okay, sorry I went over. But yeah, the proofs of things I didn't say are in the slides.